Okay, this is a looping specification. It's going to be a little harder to wrap our heads around what's going on here. It's in test control flow looping spec.k, and this is the sum to n program for some symbolic n. So similar sort of setup. We have our looping spec syntax module, which declares a bunch of variables we can use in our specifications. And the verification module, which we're going to use as our def module for doing verification in. And then we have our specification module, which contains our actual loop and stuff like that. So we have a loop, which is while 0 is less than some variable n. This is a program variable, not a symbolic integer. It's just a program variable. And n starts out pointing at some symbolic. This is actually a logically symbolic variable. Yeah, I think Virgil's got that correct there. This is a logical integer variable. And then this s starts out as a logical s integer variable as well. And then the while loop is just saying, s goes to s plus n. But remember, these are the identifiers, s and n. So we still have to do the lookups and the substitutions back in and yada, yada, yada. And n goes to n minus 1. And I think most people are familiar with the formula that ends up getting written is the sum to n is n plus 1 times n over 2. That's the sum to n. And then we add on to it any additional, like s might have already been set to something before this. So we just say s goes from s to that, basically. This is only true while n and s both start out greater than 0. I don't think we actually need this restriction, but I put it in anyway. So I'm just going to run it just to show that it's true. And then I'm going to step through it to see what's happening when trying to prove this looping specification. Okay, so it says it's true. And then we can launch the proof debugger by just adding the debugger argument here. And if you're not familiar with the core REPL, I'm not super good at using the core REPL. I'm sure there's tons of things that I'm super inefficient about. But it's very helpful for debugging proofs. You can look at all the myriad of options you have here. I pretty much only use like 3 things out of all these, which is just like step F, config, and select. But you guys, you explore it in your own time. But the first thing I can do is print out what the current configuration is by doing config. And it's really ugly. It's super hard to read, right? So the REPL fortunately has been extended in a way that lets you make new commands. And so in the README of this repo, well, I think graph would be nice for larger proofs, but I'm not doing any larger proofs now. So in the README of this repo, I have this alias here where you can say kconfig instead. This is from Ricard, actually, this idea. And what it'll do is take the config command and pipe it into cast in order to output some pretty format. Okay, that's much better, right? So what it's saying is, okay, you're in state 0, that's here. And the current configuration is this, which is the generated top cell. You got your while loop at the top that looks familiar. It's expanded out that ... into the associative list with the dot var in there. And our memory starts out how we said it would with the symbolic n and s on the left-hand side. And we also have our side conditions that we specified, which is that both s and n are greater than or equal to 0. So nice. And it's good stuff. So what am I going to do? I'm going to say step F. And it's going to say, okay, I took a step. I do config again. And now I'm in this state where it's taken the rule for the while loop. It's taken this rule here and expanded out into this if. So now I have this big if here where it says, if 0 is less than n, which is the original thing on the while loop, then execute the while loop once and then go back to the top of the while loop. Otherwise, you're done. Great. So I'm going to do step F again. And it said, okay, I took a step. And now what it's trying to do is evaluate this 0 is less than or equal to n. So you notice we get our freezer here on the top of the cell. So a a heating rule applied. This is the freezer for the if statement. And it's holding all the other arguments for the if in place for us so that we don't lose them to some unfortunate accident or something. And otherwise it says, okay, we're focused on the 0 is less than n. So we do step F again, config. Okay, now it's done another freezer. It's pulled out this $n and said we need to figure out what $n is. That's good stuff. We'll do another step F, config. And now it's looked up the $n. So notice in this previous state, it had $n at the front of the case cell. And then it did the actual map lookup and replaced it with the symbolic integer n from the memory. So that's also good stuff. That's actually an integer. We declared that n is an integer. So when we do another step F, it's now able to apply that cooling rule and put it back in as 0 less than n, right? So do another step F. And it, actually, I don't know what just happened there. Does anyone know what happened, what changed between these states? Because the only difference I see is the sort annotation. Maybe a semantic cast got removed, but I'm just going to do another step F and pretend. Oh, less than got updated. You're right. Okay. Good call. And then now that that's an integer, it can be cooled back into the if expression. So this is our Boolean. So this is a K result. Okay. Now I'm going to do a step F, and it's stopped because it's saying there's probably a branch, right? I don't know how to get it to be. There we go. If you just do a normal step, it's saying stopping because there's a branch on 8 and 9. Okay. So what that means is I've reached a point where the execution splits, and I can tell you exactly how it's splitting. It's splitting on these two rules right here, which is saying like, okay, perhaps, 0 is less than n, which is possible because over here we say that n is greater than or equal to 0, and that means n could be 3, right? And so 0 could be less than n. But also perhaps 0 is not less than n, which means that n is 0, right? So it's not able to choose which of these branches to do. So if I do like select 8, then I've taken one of the branches, don't know which, and that's the branch where the if statement was true. So 0 is less than or equal to n, right? So I can go back, select 7, go back to the previous state. And now I can do select 9 instead. So I'll do my step. And it says, okay, your branching is on 8 and 9. So I'll do select 9 instead. And this is the branch where it says actually false. It's not less than 0. So I'm going to go ahead and discharge this branch by just stepping forward again. So the rule for the empty block is this one. Step F. Okay. Okay, step F again. Okay, so it completed that proof. And how is this a complete version of this proof? Well, let's take a look. We have, because of this side condition, because we decided that that if statement was false, that 0 is actually equal to n, right? So if 0 is equal to n, then this was 0 all along, and indeed it just goes to 0 here in the n. And 0 is equal to n, this ends up being 0, and so we just have s right here. And so indeed, it's okay to discharge the proof on this branch with just n and s without any updates to them. In reality, n is 0, and s is just s, or s plus 0. So great. Okay, let's go back to the true branch. So I'm going to go back to 7 and step and select 8. Config. Now we're in the true branch. This is where things get a little weird. I'm going to step forward a bunch at a time. Oh, it looks like maybe it's branching, which is, oh, it's branching on the strictness attribute, actually. That's really annoying. Look at this, because both s and n here at the front of the case cell are variables that need to be evaluated, it's branching on, do I try to evaluate s first or do I try to evaluate n first? So if we take config 16, it evaluates n first and saves s for later. And if we instead go to state 17, it's evaluating s first. The result ends up being the same, and that's really annoying that we're getting that branching. So I'm actually just going to get rid of that branching. I'm going to say that plus is seek strict, meaning that it always chooses the first argument first, and then the second argument. And I should also do that for minus. Well, minus actually doesn't matter because our particular instance of minus here has already an integer in the second argument. And that should get rid of that branching on that strictness operator for us. I'm actually going to compile this. Does everyone understand why that branching happened? Because of the two heating rules that happened? Oh, I have to. I remember when you restart your REPL to define your config alias here. I pretty much never use this REPL without having this alias. Okay, so we're back at this branch point, which is the if branch point. So I'm going to select 8. And we've taken the through branch. So step F4. So now we're back at S plus N here. And now I'm going to do a step, and it didn't branch that time, right? Instead, it heated out the S directly because that was the first one. So I'm just going to keep stepping forward in larger increments until we get to where we're at the while loop again to show you how case circularity reasoning works. Okay. Okay. Okay, so we're back at the top of the while loop, and we need to be able to prove that, this, our proof doesn't say that we're allowed to reach the top of the while loop and then we're done. What our proof says is that we have to finish executing the program. And when we execute the program, what needs to be stored here is the sum, right? But that's not what's here. And if I actually were to take another step, I would assume it would be done, but, oh yeah. All right, so I take another step and the while loop's gone, right? So look at that. I went from the while loop being here, the current n being n minus 1, the s being s plus n. I went from that state to the while loop being totally gone, right? That doesn't follow our control flow of our execution at all. And what happened is it got to this state, which is state 29 right here, and it saw, hey, this state is actually a more specific instance of the left-hand side of the thing I'm trying to claim already. And so I can just assume the thing I'm trying to claim and step directly to the end at that point, right? That's a little bit confusing, but let's see what that means. I'm going to make a duplicate of this state. So the state we're in, and I'm going to rename variables for clarity. S is going to be Z, or no, M. M is back to Q. And N is going to be R. Okay. So this is the state we're in. We've not quite though. N goes to that's N. And S is R plus Q. Okay. And that's R is greater than or equal to 0 and Q is greater than or equal to 0. Okay, and we have that, not only that, we have that Q because of the if branch that we took. Okay, so this is the state we're in immediate right here. And I've renamed the variables. N is now Q and S is now R. I'm sorry if that's confusing, but it's just confusing to be able to talk about the rule with the same variable names. And so we have to decide, is this rule, is this state actually matchable by the left-hand side or unifiable with the left-hand side of this state right here? Okay, well, if we pick the binding that variable S is bound to R plus int Q, and the binding that variable, so that's this variable S here, right? And this variable N is bound to Q plus int minus 1. Now we need to check, do these side conditions hold, right? So we need to know, okay, is N greater than or equal to 0, which means is Q plus int minus 1 greater than or equal to 0? Is that true? Well, actually, we do know it's true because Q is greater than 0 in this case because we took the true branch of the if statement. So Q minus 1 greater than or equal to 0 is true. So that's good. We also need to know, yeah, matching only against the left-hand side of this claim right now. I'm ignoring the right-hand side for now. I'll talk about the right-hand side in a little bit, but I'm just seeing, are we in a state here where if we were to assume that this claim was true, can we just take it and shortcut straight to the finish of the proof? Yeah. And then we need to also check the other side condition of the claim. S is greater than or equal to 0. We decided that S is R plus Q to be able to do the matching. So is R plus int Q greater than or equal to 0? Well, we know that R is greater than or equal to 0 and Q is greater than or equal to 0. So the addition of them will be greater than or equal to 0 as well. Yes. So we are able to match the left-hand side of this claim, which I'm kind of highlighting, and the requires clause is satisfied. And so using that substitution and this state, we can jump straight to the right-hand side of the claim, which is the state that is dot on the case cell and dot, dot, dot. Right? That's this part right here. And then these, we have to substitute in our values for S and N. So that's mem, $S points at what S is, which is R plus int Q plus int. N is Q plus int minus 1. So okay, I know that's a big expression, but if anyone disagrees with my assessment or my substitution there, please speak up so I can try to make sure it's correct and try to explain it. But basically, I just took the right-hand side of the rule and put my substitution for these things in to construct my new right-hand side or my new state. And then N, the right-hand side now goes directly to 0, actually. So this is the new state that we can jump straight to. And we get to carry over what we know about our variables, which is these things, right? So jump straight through to the right-hand side of the state. So we're going to go ahead and simplify this a bit, just using some common simplifications we know. R plus int Q plus int Q, this thing is a plus and a minus, and it's real annoying to have all that stuff going on. So we're just going to get rid of this plus and this minus here, cancel those out, and now we can have something that looks like this instead. Okay, so now it's up to the SMT solver actually to determine if this expression fits the correct form. No, actually, no, it already fits the correct form. We're done. Yeah, we're done. No, are we done? No, we're not done. We have to now, well, Yeah, we're done. Okay. Well, we're in the right-hand side of the claim now. The SMT solver probably needs to decide that this is actually fitting this form, given this substitution down here, which it is, in that substitution, which it is because we're doing Q times int Q minus 1 plus int Q over here, which could also be written as just that, which is exactly what we need. I don't know how the SMT solver is able to figure that out, but I guess it is. So let me go ahead and put both those so you can see the simplification. Right. So this state simplifies down to this state, which is a step that Z3 takes, I guess. I don't know how it's able to figure that out, but they're magic, so I'm not going to focus too much on it. Okay, so the whole point of that is we were trying to prove this thing that could loop forever. We get to a state that looks like our initial state again, but the variables have changed slightly, different substitutions. That's this change right here. We somehow go from S to R plus Q and N to Q plus 1, but otherwise we're on the same as the left-hand side of the state here. Then we can immediately use this rule as if it was a lemma or a claim in our semantics to step to the final state without having to execute the loop again, basically. So that's how we're able to prove these kind of infinite looping specifications, is using this co-induction thing. So Brandon knows all about that. He wrote the paper on it, basically. So if you have specific questions about co-induction, you can ask him.